When you've completed this lesson, you should be able to read and interpret exponential graphs on linear and semilog scales, graph exponential functions on semilog scales, read and interpret polar graphs, and you can build a graph with those coordinates and convert back and forth from rectangular to polar coordinates. You're going to encounter a wide range of data in your photonics career, relationships that are linear, exponential, and polar. And the best way to look at that data is often on a graph. Now, sometimes linear graphs work, and sometimes logarithmic scales are a better way to present the data, and sometimes polar charts are the best. Technicians need to be able to draw, read, and interpret all of those different kinds of graphs. So, for example, if you're examining the fall-off in light intensity from a source, since the intensity varies with both the distance and the angular position around that source, a polar graph of r versus theta is the most helpful type of graph to use in that type of situation. But before we look to that, let's look at an example scenario that a photonics technician might solve. So you might have a fiber optic cable that's carrying light whose performance varies with the wavelength of the light. Notice here that we have a graph of the varying losses that occur at the various wavelengths. But the scaling on the vertical axis is not like we've seen before. This is called a semilog scaling, and we'll learn more about that in this module. So looking at this graph, can you tell what is the power loss per kilometer of this cable for light around about 800 nanometers or 1550 nanometers? And at what wavelength does the cable present the highest loss in power per kilometer? And what is the value of this loss? Well, let's spend a few minutes reviewing important types of graphs before answering these questions. When we graph exponential functions, they're different than linear functions. They do not have a constant slope. So let's consider a common electrical relationship, which does have an exponential relationship. Here we have the voltage of a capacitor that is charging, or in this case, discharging through a resistor. V is the voltage across the capacitor. V0 is the battery voltage, which is initially used to charge that capacitor. R is the resistance in ohms, and C is the capacitance value, and T is the time since the charging, or in this case, discharging began. So let's look at the exponential function a little bit closer. So if we have a 10-volt battery charging at 250 microfarad capacitors, and is being slowly discharged through a 2 kilo-ohm resistor when we close the switch, then the capacitor's voltage can be measured over time, as we've shown here. So at time 0, it exactly equals the battery voltage, and so the ratio of V over V0 is 1. But then as it begins to discharge, the ratio begins to drop closer and closer to 0. Let's consider a graph of these ordered pairs. You can see that it drops very rapidly at the start, and then it sort of flattens out more slowly as it approaches 0. Well, that's a very important process, and that process is called exponential decay. And you'll encounter things like this often in your photonics career. These values approach 0, in this case, asymptotically. That is, it gets closer and closer to 0, but never quite gets there. So if we are to zoom in on that portion of the graph on the tail end there, we'll see that it's not yet 0. And we kept going past 2 seconds to 4 seconds, it would never quite reach 0. Well, the rate at which it decreases depends on the value of R and C. And if you look at our formula in the exponent, we have T divided by RC. So if we have a large RC value, then the curve is going to be much flatter than it is right now. If we have a smaller RC value, then that curve will be much steeper. So R and C seem to have a very important effect on the shape of our exponential decay graph. Now, the product, RC, is known as the time constant, or tau, the Greek letter tau. T-A-U is the way that it's spelled. And we can rewrite the discharge equation using that as tau, that product of RC. So V over V0 is equal to E raised to the minus t over tau power. The time constant is a very important parameter in exponential decay problems, just as slope is important in linear functions. Now let's look at logarithmic functions, which are somewhat related to exponential. The intensity level of sound is modeled by a logarithmic function. So perhaps you've heard about sound levels and decibels. Well, this is a formula that we use to calculate the decibels is equal to 10 times the log base 10 of the ratio of the intensity that we measured in watts per meter squared divided by the threshold of hearing, the very, very low intensity level of 1 times 10 to the minus 12 watts per meter squared. So from measurements of various sound intensities, we can produce a table just like here, where we have the intensity that's measured, the I values, and the IL, the intensity of the values. You can see at the hearing threshold, the IL value is equal to the log base 10 of 1 times 10 to the minus 12 divided by the threshold divided by 1 times 10 to the negative 12. So that's the log of 1, which happens to be 0. And as we get louder and louder and louder, the intensity levels increase. So we can try to graph these values on a linear x and y axis. We can graph from 0, 0.2, 0.4, 0.6, 0.8, or up to 1, our highest intensity, versus our intensity level, which is those log values. And we see here that almost all of them are right up against the axis. They're all very small until we get to the last value. And that's not a very useful graph to be able to interpret. The problem is that most of those x values are so small that they appear to be 0 on this graph. Even if you dropped the largest value and just started with the highest one of 10 to the minus 4, they'd still be right up against the y-axis. And so we need a way to be able to somehow spread those out. You need a different type of scale on the x-axis. Now the solution to that is to recall how the logarithmic function took very large numbers and returned the power of 10. Since the I values are so large, we could plot the log base 10 of I instead and reduce the effects of having large and very small values on the same graph. So here we have an even easier solution. Instead of taking the log, we'll just use logs down here, the powers of 10. Instead of 1, 2, 3, 4, 5, we'll use the power of 10. So we'll start with the biggest value of 1, and the next one will go down to 1/100th, or in this case, 10 to the minus 2, and then 1 to the 10,000th, and so forth. So we'll see here that our horizontal axis is actually logarithmic in nature. It's not linear. And when we do that, we get a straight line relationship almost. One of the values departed a little bit, but our exponential relationships will appear as a straight line. Let's look at another example of a semilog graph. So let's look at the tables of values here. These are clearly a power relationship, right? So 10 to the 0 power, 10 to the 1 power, 10 to the 2 power, 10 to the 3 power, 10 to the 4th power, 10 to the 5th power, and 10 to the 6th power for x's of 1, 2, 3, 4, 5, 6, 7. So clearly this is a power series and not a linear relationship. So you know that if we graph that on a linear graph, things would look very awkward. So let's look at those two graphs and compare them. So here's what happens on a linear graph. If you try to scale the y-axis so we can get the largest value on there, then all the first 5, even almost 6 values are essentially on a straight line. And that's really not telling us a whole lot on that graph. So that's the problem with the linear graph in exponential types of functions. So now we can look at a different kind of graph, as we've seen on a previous example, a semilog graph. the scale on one axis is no longer linear, but is now logarithmic. So we have the powers of 10 instead. So now when we graph our data, you'll see that it's in fact a straight line. And now we can do things like interpolate and so forth between those points, and it's actually meaningful. So the semilog graph is much easier to interpret. We call it semilog because only one of the axes is logarithmic. There are cases where both the x-axis and the y-axis are both logarithmic scaled, and that would be called a log graph paper. And when you only have one of them that's logarithmic, either the x or the y-axis, then you would call it semilog graph. Okay, so let's turn our attention to a different type of graph, a polar graph that represents data on a polar coordinate system. So you've seen the Cartesian coordinate system. That's a rectangular grid of x and y ordered pairs, where we plot the x value and the y value, and we determine the location of a point. And here's another important system called the polar coordinate system, which basically looks like a big dartboard. And you'll notice in the center is where we start, and if we move out, we'll have 1 unit or 2 units or 3 units, and this will tell us how far out the r value should be for our first coordinate of ordered pairs. The second coordinate in our ordered pairs is the angle, and that specifies how far around the circle we'll plot our point from some sort of zero reference line. So usually we'll have a line that stops right about here at our 3 o'clock position as our reference for 0. But you can find polar graphs that'll use due north as the 0, for example, or any other angle as a reference point. With this coordinate system here, you can locate any r and theta value by simply locating, going out from the center, distance r, and going around the circle, some angle theta. You can orient and label a polar chart in many ways, but as we said, we will always start with 0 at the horizontal 3 o'clock position there, and we'll use in this case a scale of 1, 2, 3, 4, 5 for our r values, and you can just as easily use 10, 20, 30, 40, 50, or 2, 4, 6, 8, 10, or whatever it is that you'd like, but just as you can on a Cartesian coordinate system. Now, some polar coordinates, let's look at the graph of those. R and theta equals 3 and 0. So we didn't move up at all on the angled value, but we went out r equals 3. How about r equals 4 and theta equals 45? So we'll go out to the 4 on the 4 position on the scale, and we'll go around 45 degrees. Or 2 and 150 degrees. So you can go all the way around to the other side and get coordinates there. How about 4.5 and 230 degrees? So you see, you don't have to fall right exactly on the ring, just like you can on a linear coordinate system. You can go in between the lines, and we've done that here with 4.5 and 230 degrees. Or we can get really strange results like r equals the square root of 14 and negative 71 degrees. So how are we going to handle that? Well, negative 71 is going backwards, and we can also compare that to 360, which will be the same as 289 degrees, and we can evaluate the square root of 14 and get 3.74, and that tells us how far out from the center we have to go. Or how about 5 and 480 degrees? So 480 degrees, that's more than 360, so we have to go around more than once to get over. So really, we're just stopping at 120. Now, in real life, you seldom encounter angles that are greater than 180 degrees, so we'll not deal with those anymore in this module. You may have an XY ordered pair, but you want to plot it using polar coordinates, r theta. In polar coordinates, the r value indicates the distance from the origin. So let's consider the xy point as 3 and 4. Well, how far is that from the origin? Well, when you're plotting that, you probably should have been reminded of a right triangle. It has a leg of 3 and a leg of 4. And you know how to find the distance between the origin now. That's just the hypotenuse there in the right triangle. So that's just the same as the Pythagorean theorem can tell us that r squared is equal to 3 squared plus 4 squared. Or in this case, r is equal to the square root of 9 plus 16 is equal to 5. But that is the value for r. In general, for any x and y then, we have that r is equal to the square root of x squared plus y squared. To find the angle theta, we can then again use our right triangle that we learned about in trigonometry, where we have the angle theta for that coordinate is related to the angle, the opposite side of 4 and the adjacent side of 3. So that probably clues you in right away that it's related to the tangent of that angle. And we can take the tangent then is equal to the opposite over the adjacent, or in this case, y over x, y divided by x. So in that case, 4 divided by 3 equals 4/3, or we'll round it off to about 1.33. And the inverse tangent of both sides will be able to tell us what the angle for that is, and that'll come out to about 53.1 degrees. So we can say that the xy coordinates of 3, 4 is equivalent to the r theta coordinates of 5 and 53.1 degrees. In general, then, for any xy, we can convert to polar coordinates by using r is equal to the square root of x squared plus y squared, and theta is equal to the tangent inverse of y divided by x. We have to caution you, though, by using the inverse tangent function outside of points that lie in quadrant 1. So you'll recall in our geometry and graphing units, we talked about this as being quadrant 1. This is where all the x and y values are positive. And over on the left-hand side, we'll have negative x values and positive y values. In quadrant 3, we'll have negative x and negative y. And over in quadrant 4, we'll have negative y and positive x values. Now, as you use the tangent functions, and we take 3 divided by 4 and take the inverse tangent, we have 53.1 degrees. And if we were down here in quadrant 3 and we had negative 3 and negative 4, and we took the tangent of negative 3 divided by negative 4, we would also have 1.33, and theta would also come out on the calculator as 53.1 degrees. But that's not 53.1 degrees, is it? So the moral of the story is you have to be very careful when using that inverse tangent function outside of quadrant 1. Okay, so suppose we have an r and a theta value, and we'd like to convert it to rectangular coordinates. So if we have some data point out here, which is some distance r from the origin and up some angle of theta, then how can we find the x and y value for that coordinate? So again, we'll notice the right triangle, the opposite and the adjacent sides, and theta. So we know that opposite is really the y value for that coordinate, and the adjacent is the x value. So let's look at the adjacent side. So we know that there's a ratio called the cosine ratio, which is the adjacent side divided by the hypotenuse length. And the hypotenuse of the triangle is r, and the adjacent is the x value that we're looking for. So we can set up the equation and solve for x. So we know what x over 13 equals, which is the cosine of 22.62. We can put that in our calculator and calculate 13 times the cosine of 22.62 will equal 12. So our x value will equal 12. Similarly, on the y-coordinate, we have the sine ratio, which is the opposite over the hypotenuse, or in this case, y divided by 13, our r value. And we can calculate the sine of 22.62 and multiply that times the r value and get 5. So now we know that the r theta value at 13 and 22.62 is equivalent to the xy coordinate of 12 and 5. So in general, we have that x equals r cosine theta and y is equal to r sine theta. Now let's practice doing some of that converting. So here we show you the summary of all of the conversion formulas that we've just discovered. We'll convert r theta of 7 square roots of 2 at 315 degrees to xy. So if we simply just apply the formulas that we have above, that x is going to equal r cosine theta equals 7 square root of 2 times the cosine of that angle. That'll calculate out to 7. And the y value is equal to the r sine of the angle, which is equal to 7 square root of 2 times sine 315 degrees equals negative 7. So r theta is equivalent to xy of 7 and negative 7. Now let's convert xy of 3 and 5 to r theta to polar coordinates. So we have x equals 3 and y equals 5, which we can substitute into the formula of r equals the square root of 3 squared plus 5 squared, and that evaluates to 5.8. And similarly, theta is equal to the inverse tangent of y over x, which equals the inverse tangent of 5/3, which comes out to about 59.0 degrees. So we have our xy point is equivalent to the polar coordinates of 5.8 at 59.0 degrees. Now we're ready to look a little bit at our opening scenario where we have the graph of the semilog scale. So what is the power loss per kilometer of this cable for light at 800 nanometers? We'll notice that the logarithmic scaling on the vertical axis so that we know how to read that y-axis, and we'll notice that we have 3 decades. The first decade's tick marks corresponds to 0.1, 0.2, 0.3, 0.4, 0.5, up to 1.0. The second decade tick marks correspond to 1, 2, 3, 4, 5, and then jumps up to 10. And you can see here that the next decade would be 10, 20, 30, 40, 50, up to 100. So now we're ready to read that graph just like we do any graph. So you find 800 nanometers on the x-axis and go over to the y, and we'll see that we're just above the second tick mark, which we know means 2. So we're going to estimate about 2.2 decibels per kilometer loss and 800 nanometers. At 1550 nanometers, we come up and go over, and we're much lower on the graph scale at 0.22 decibels per kilometer, or about 1/10 of the loss at the shorter wavelength. So there's a big difference if we factor 10 difference between those two numbers, even though they all fit on the same graph. All right, so what wavelength does the cable present the highest loss in power per kilometer, and what is the value of that loss? Well, the highest loss is going to be at the peak at that absorption where most of that signal is absorbed or lost, and that occurs if you come down to the x-axis at about 1380 nanometers, somewhere a little bit below 1400, and what value is that lost? So how much is lost at that point? So we'll have to go over to the y-axis like we did before, and we come over and it's about somewhere between 10 and 20, so we'll estimate that it's about 15 decibels per kilometer. So you'll notice that reading a semilog scale is much different than reading a linear scale, and it'll take some practice to do that, but we'll get really good at it as you continue to learn what those tick marks stand for. So now we're ready to tackle some of the practice exercises in this unit. So let's look at the data in the capacitor of the electric circuit that's discharging, just like the one that we saw in this example. And we're going to graph the data on a semilog graph, making the y-axis logarithmic. What scale should we use for the x-axis? Well, the x-axis will be time, so we'll just use a linear scale divisions running from 0 out to at least 2.0. And divisions of about 0.2 should do very nicely here. So what about the scale for the y-axis? Well, log scales start at some power of 10 and then increment up to the next decade. So our smallest decade will start at about 0.01 or 10 to the minus 2, where that's where our lowest values are, and our highest values will need to get all the way up to 1.0 or 10 to the 0 power. So we're going to have to span our logarithmic scale from 10 to the minus 2 to 10 to the minus 1 and up to 10 to the minus 0 power. And here we have our graph. So we've started our y scale at 0.01, and we go up to 0.1, and we go to 1.0. And we've plotted our data as it's discharging down, and you see that we have a straight line and not that exponential curve that we saw in the earlier examples. And here are the tick marks, if you notice, at 0.01, 0.02, 0.03, 0.04, and 0.05, and so forth. Notice how they get closer and closer together as we get closer and closer to the next decade. And then they spread out again. So here we have 0.2, 0.3, 0.4, 0.5, and they get closer together again as we get to the end of that decade and we start the next one. So that's very characteristic of logarithmic scales. And so you'll learn to recognize that right away when you see a scale that gets all scrunched up as it gets closer to that decade. And that's a good sign that you're looking at a logarithmic scaled graph. We call that a semilog scale because one of the axes is logarithmic and the other is linear. And you will encounter sometimes where both the x and the y axis are logarithmic, and in that case you don't call it a semilog, you call it log-log paper. Now let's look at the sound intensity, IL, in decibels using this relationship. So you may have heard of so many decibels of sound intensity, and this equation provides us with that value. So 10 times the log of the intensity measurement divided by the threshold value, I sub 0, as we saw in the text. So let's calculate the IL values for ratios of 1, 10, 20, 30, 40 to 100. So substitute the ratio values and use your calculator. So 10 times the log of 1 is equal to 0. That's because the log of 1 is 0, so 10 times 0 is 0. 10 times the log of 10 is 10, because the log of 10, base 10, is going to be 1 times 10 is 10. So those were easy, wasn't it? Now this one's not as easy. You're going to have to use your calculator for this. The log of 20 is about 1.3, and when you multiply that by 10, it comes to 13. Log of 30, log of 40, and so on. And you can go on and finish that data. And here's what your table will look like when you're done. So now you're asked to graph the table of values on linear axes. So what scale should we use for our x-axis for the I over I0 ratio when we're ranging from 1 to 100? So we could use a linear scale from 0 to 100 going from increments of 20, or for our y-axis we can go from 0 to 20. And we'll use a linear scale with divisions of about 5. So 0, 5, 10, out to at least 20. And here's what our graph might look like. So our x-axis and our y-axis. And you can see here where it's kind of like an exponential curve. And this is asymptotically approaching some limit. Now let's graph those same values on a semilog axis using a logarithmic scale on the x-axis. The x-axis is, of course, the ratio of I to I0 values. And what scale should we use for that? Well, we need to start with 10 to the 0 power and get 1. And that'll be our smallest value. And then our second decade is starting at 10. So 10 to the 1 and needs to end at 10-2 or 100 in order to get our value of 100 in there. So most of our data is going to be plotted in our second decade, as you can see. So what scale for the y-axis? Well, we'll just use the same as before, between 0 and 20 in steps of 5. So now we have our logarithmic scale on the bottom here, and you'll notice that the characteristics compressing on the grid lines as we get closer and closer to the end of the decade. And our values in this case are not a curve, but a straight line, which is indicative of a logarithmic or exponential relationship of x and y. And here's for reference purposes, the tick marks could be labeled 2, 3, 4, 5, and 20, 30, 40, 50 in this case. And typically you don't label them between 5 and 10 or 50 and 100 because they get closer and closer together, so you wouldn't label them. And it's really hard to get those numbers in there. All right, so let's look at an example of a polar relationship of coordinates in a polar coordinate system. So we have measurements of light intensity are taken at various distances and angled positions from a light source. As our illustration in our text shows, you have a light source that's up against a wall, and we're going to measure light all around at angles of 30, 60, 90, right in front of the light source and around to the other side of 180 at different distances from the source, 2, 4, 6, 8, and 10 centimeters away. And we're asked to graph the locations of the measurements at 2, 6, and 10 centimeters on the polar coordinate system. This is simply going to show you where you stood to make your measurements, or where you placed the sensor to make your measurements. So for now, we're going to look at the actual positions where the measurements were made, not the measurement values. So we're going to position our angles 0 degrees at 3 o'clock and 90 degrees at 12 o'clock, just like we saw in our example in the text. And our values will range from 0 to 10 centimeters. And so we will scale our radio axes of 0 to 10. And so here we'll plot all 5 sets of polar location data instead of just 2, 6, and 10 centimeters that we were asked to do, because it's pretty easy to do with our graphing software that we have. So we've produced this. Here you'll see the legend or key that shows which color corresponds with which distances. And at 2 centimeters, we have which is real close to the source, which is right here at the center. And we measured at 0, 30, 60 degrees, 90 degrees, 120, 150, and 180, all at 2 centimeters away from the source. Then we measured it at 4 centimeters away at these locations. And we measured it at 6 centimeters away. We measured at 8 centimeters away. And lastly, we measured at 10 centimeters away. Just as we would connect dots on a Cartesian coordinate system, we can connect the dots with a smooth curve on a polar coordinate system. Now let's look at a probably more standard way of a polar chart. So that would be the intensity way, which is a lot more interesting in this case, because we see our intensity values are not the same as we go around different angles. Now, polar charts are very commonly used in optics, radio, medicine, acoustics, and so forth, all of these other fields of study, which are very useful to look at angular dependence of measurements. So we're going to graph the fractional intensity versus the angle theta, and we can compare those graphs at various distances r. Now, don't confuse them with the r in this case with the notation of r with theta. So we're going to use a fraction of our light intensity graph to show the radial coordinate. And here's what the graph will look like. Look at our legend here. We have that the blue dot corresponds with 2 centimeter measurements. At 2 centimeters, we have a very high fractional source of 0.25. We measured 1/4 of the intensity of the light right there, right next to the source, and it's way out here. And if we step out at 4 centimeters away, there's a big reduction in the light intensity. And 6, 8, and 10 are even smaller. In addition to the relations between the close distance and the farther away distance, you'll notice that it's not uniform. It's a little bit greater intensity that's evident right out in front as it is off to the sides. So you can see a little bit of a forward favoring of our light source. So now, what do you notice about the intensities as they relate to angle and distance? Well, since the intensities are relatively constant at each distance, we can average them over all of the angles, so we can add another column to our table. and we can look at a rectangular plot on our Cartesian coordinate system of a fraction of the light intensity, the average in this case, versus the distance from the source. And we see a nice smooth curve that looks like it's exponentially decaying, right? So this is actually what we would call an inverse square law in action here. And you've probably heard of that before, where the light intensity falls off in proportion to the inverse squared of the distance from the source. Now, in exercise 4 asks us to do some practice conversions from polar to rectangular coordinates. So let's convert 17 at 81 degrees to rectangular coordinates. So as you've seen in example 4, we would use the relationship r and cosine theta. So 17 cosine 81 degrees, evaluate that to 2.66. And if y is equal to r sine theta, that would be 17 times the sine of 81 degrees, which would be 16.79. Now, it's always a good idea to check that out with a sketch. And so we'll make a quick sketch of our point that's out at 17 units and 81 degrees up. And sure enough, it looks like the x value will be a very small value, less than 4, probably 2.66 is about right. And the y value is up there. Well, it's almost 17, so 16.79 is about right. So we're confident that we've probably done our calculations correctly. So xy is equal to 2.66 and 16.79. So let's go the other way. Let's convert our rectangular coordinate to polar coordinates. And we're given 32 and 9 for x and y. And we'll use the other set of conversion equations from example 4, which will be r is equal to the square root of sum of the squares, in this case 32 squared plus 9 squared, and we'll have a result of 33.24. Similarly, theta is equal to the inverse tangent of 9 divided by 32, y over x, and that'll evaluate to 15.7 degrees. And once again, let's look again at our sketch quickly to see if it looks right. So we go over 32 and up 9, and that produces a dot out there. And it looks like the r value is going to be at about 33, a little bit longer than 32, because that's the longest side of that right triangle. And it looks like we're up at about a small angle, just up at about 15, 16 degrees. So that seems like it works. So we're confident that we've done our calculations correctly. So r theta is in fact 33.24 and 15.7 degrees. All right, and that concludes our treatment of special graph in Module 11, and I know that you're going to have a lot of confidence now to go on and use those skills that you've learned in this module as well as all the other modules in your photonics career, and maybe we'll see you again. Take care.